All right, so let's see. This number 23, now let's see what we're doing on this one. The problem gives you this information. It's saying that you're going to calculate the work, so you got to find the work required to stretch a spring 0.5 from the equilibrium position, and you're doing Hooke's law, okay? Now remember what work is, think of it this way, it's a force that it's applied to something over a distance, okay? So the first thing that we probably want to do on this for part A is on part A they're saying that a spring requires a force of 50 newtons to be stretched 0.2 from its equilibrium position. Whenever you do work, now first thing I'm going to do is just kind of write down the formula for work. Work was an integral we talked about last time, so you're just doing an integral from A to B of f of x times dx. Okay, and remember what this represented is that was the distance. So like if you're talking about a spring, that would be the distance that's stretched or compressed, and that's a infinitesimal distance. We're kind of chopping that up, and then the force would be whatever's applied to that. So that's a product of the force and the distance is what that is in. Okay, so what you got to do on part A on this particular problem is the first thing you need to do is you need to work with Hooke's law. So Hooke's law is pretty easy to remember. That just goes like this. The force f of x is just equal to k times x. And one of the things you got to do on this is generally you got to figure out what that constant k is. And they've given you enough information on this then to figure this out. So what they've done is they've given you have a force of 50, so that's going to go there. They've given you that it's stretched a distance of 2 from the equilibrium position. Okay, so just plug that in and then you can find k. So f of x is going to be 50 newtons. Okay, and then k, then you're going to have 0.2 like that. And then the units are working out. You don't have to worry about the units too much. You have a newton and you have a meter. That's the way the units are supposed to work on these things. So you don't have to worry so much about units. Then you can divide both sides by 0.2. And then you can take your calculator if you need to and crunch out what that is. So I think when I did that, that is 250 it looks like. Okay? So what that means is what you get from here on this first part right here, that means that you get this force function. You get f of x is equal to 250 times x. And again, that comes from Hooke's law. So you have to figure out that thing first before you start going through and computing the work then. Okay? So that's how you're going to go about doing that. Okay, then the second thing that you got to do, so after you've got this, that's the first thing, and now the second thing you do is now you're supposed to find the work when it's stretched, and then this time on part A, what it says is, okay, you got to look at the directions to the problem. It says calculate the work when you're stretching 0.5 from equilibrium position. So now you do your integral. So what you do is you do your integral. Okay, equilibrium is where? 0. Okay, that's at the beginning. You're stretching, we said 0.5. What if we were compressing? What would we say? Negative. Okay, got to think of that. You're starting from equilibrium position, so it's 0 to something. Stretching's positive, compressing's negative. You got to use those elements when you do that. And then your function is 250x like we have times dx, okay? And you guys have worked out a lot harder integrals than that, so that's an easy one to work out, okay? All right? And that's what you'll find in this section. The integral is going to be a little easier. So the antiderivative would be 250x squared over 2, and then you're going to evaluate that from 0 to 0.5. And then this will be 125x squared when you reduce that from 0 to 0.5, and then you just calculate that out with fundamental theorem. So let's see what we get. We'd have 125 times 0.5 squared minus 0 squared, and then that would be 125, and let's see, that's what, 0.25 minus 0, so then if you work that out, that is 331. Check my arithmetic on this. Some of this I did earlier, so we got 31.25. Okay, what are the units for work? We talked about that. A joule, okay? So you have a joule. So you want to write the units in there, so that would be the answer to the problem. Okay? All right, you study physics, you'll learn to do a little bit of this stuff right here. But Hooke's law, generally, you start by finding whatever that constant is. That's the idea. Okay? All right, so is there any question about anything with that? The integral should be real simple. But, you know, the setup of Hooke's law is what we're kind of getting through. Any questions? Okay? All right, very good. Okay, so let's go to the second part of this then, this part B. And let's see, this time, now we've got Hooke's law set up and everything. So this time it says we have a spring that requires 50 joules of work, and it's going to be stretched 0.2 from equilibrium position. So ultimately in this problem, we do the same thing. So ultimately in this problem, we're going to find the work when you stretch the spring 0.5 from equilibrium. That's ultimately what you do. But you have to start this by this. What they've really given you is they've given you that the work is 50 joules. Okay, they've told you that. And then they're saying that that distance that it's stretched, which would be x, would be 0.2 meters from equilibrium. Okay, so you actually got to set up an integral, and it's kind of like an integral equation on this. So the way I'm going to start on this is let's just write down the work formula. The general work formula is the integral from a to b of f of x times dx. And let's just kind of see what we have going on in this problem then. So basically what I see is they gave you the work. So you're going to plug that in like that. So that's going to be 50. And don't worry about the units. You have joules and you have meters. That's the key thing, because a Newton is a kilogram meter per second squared. So you got to have meters in order to match up the units. So everything matches on this. Okay, now we're stretching the spring from equilibrium. So how do your limits go? 0 to 0.2. Okay, like that. And then what you have on this is you have f of x. But f of x, according to Hooke's law, is kx. So what you're going to do, instead of putting f of x there, put kx times dx like that. And what that'll allow you to find is it'll allow you to find k. And then we can build our function, because ultimately what we got to do is we got to know this function before we can find the work. Okay? All right, does that setup make sense to everybody? Okay, this time I gave work. Okay, I didn't give the function, I didn't give k, but I gave you enough information to figure it out. Okay, so that means what you have to do in the problem is you have to work out this integral. So you would have 50 here. Okay, now see, k is a constant, so you write it down. The integral of x is going to be x squared over 2, and then you're going to evaluate that from 0 to 0.2 like that. Okay, so you can do that. Now we need to use the fundamental theorem to work this out. Ultimately, we got to solve this equation for k. So we have 50 equals k over 2. See, that k over 2 is a constant, so that's not a part of your evaluation. Then you plug in your limits, so you would have 0.2 squared minus 0 squared like that. Okay, now we're getting close to having an equation we can solve. So this is 50 equals k over 2. And let's see, that would be 0.04 minus 0. Okay, so that would be 0.04 k over 2 if you did that. And if you divide that, that would be 50 equals 0.02 k when you divide that out like that. And then what you need to do on that one is you just need to divide both sides by 0.02. And that'll give you what that constant is. So that one, I didn't crunch that one out. I don't know what that is in my head. So let's see, 50 divided by 0.02, 200, 2,500 is what that is then. Okay, so we got k is equal to 2,500. Okay, all that work just to figure out what the constant is what you have to do. Okay, all right, let me pause there for a second and see if you got any questions about what I've done so far. Now see, this time you had to do, that's an equation with an integral in it. It's an integral equation. So you have enough information to work that out. So what you would kind of do is the first thing is finding k. So we've done that. The second thing that you want to do is, if you read the directions to the problem, let me scroll up to the top. Again, what you're doing is you're finding the work. So you want to find the work when the spring is stretched 0.5. Now we have all the information we need to solve the problem. So the work, again, is going to be the integral a to b f of x dx. Now we know everything. So since we're stretching the spring 0.5, then we're going to integrate from equilibrium, which is 0, to that distance 0.5. Okay? And then the function, remember Hooke's law is kx, so what that's going to be now is 2500 x dx, like that, and you're ready to finish up the problem. Okay? All right, is that making sense to everybody? Okay? All right, let's go ahead and finish this up. So this integral right here, you would have 2500 as a constant. Antiderivative of x the first is x squared over 2. And then that needs to be evaluated from 0 to 0.5 to finish up. So let's see, 2500 over 2 is what, 1250. And then you do 0.5 squared minus 0 squared when you work that out. So that's going to be 1250. And let's see, that would be 0.25 minus 0. So then I need to calculate that out and see what I get here. So 12 looks like we just need to do 1250, and then we need to multiply that by 0.5 squared, which is 0.25. And let's see, that gives 312. So the final answer is going to be 312.5. Okay, and what's the units for work again? Joules. Okay, so be sure you pay attention to the units on that then. Okay, and that's the problem. That's probably the problem that takes the most work. But notice on really the thing on Hooke's law generally is you're given a force, you're given a distance, you can use that to find what k is. And then the integrals aren't going to be too hard to work out. Okay? So this shouldn't be too bad. What do you think? Okay? You do this a lot more in depth when you study physics. We're just trying to get you kind of an idea of how integrals can be used in a different kind of context. Okay? All right, so that will wrap that up then.